Okay, we're going to look at something again you should be relatively familiar with from GCSE, and it is a decay curve. If we have a sample, so if each of these represents a unstable nuclei, and we have 16 of them there, we know that at some point in the future, if those are unstable, they're going to decay. Um, we can't tell when. With particular isotopes, it's more likely it's going to be sooner than later. For other isotopes, we know it's probably going to be a long time before they decay. We can't tell which one is going to decay first, because radiation is random in nature. Um, However, if we have a large enough sample, it then becomes predictable in the manner that that sample will decay. Okay, so I might know which of these is going to decay first, but if I have a large enough sample, um, I can get to the stage where I can be fairly confident about how long it will take for half of those to decay. I wouldn't know which ones are going to decay, but we can get a time for how long we expect it to take for half of them to decay or for half of them to be remaining. Now, when we plot either the number of unstable nuclei that remain on a graph against the time, we get this shape. And what it shows is starts off at our initial amount and it decreases. But it decreases most sharply at first because if we have got more unstable nuclei, it's likely that more of them will decay in the first section, rather than down here when we're left with very few. It's unlikely that one or two will decay in the next time period. So we get this shape of a curve. Now, we can also have this in the axes and it doesn't change the shape of the curve, so it counts per minute. Now, quite often, this is easier to measure because we just do it with the Geiger-Müller tube. That is just the activity from the source. And essentially what we're saying is there, if we have more unstable nuclei, which we say there was at the start, there's going to be a larger activity as more of them decay. And as we get down to the being fewer and fewer unstable nuclei, we should expect the activity from that source to be less. And they both follow the same predictable curve. Now, when I get down towards the end, there's maybe only one or two unstable nuclei left. It then becomes hard to tell exactly what's happening. It might not follow a smooth curve, but when you think about the size of nuclei, even in a few grams of matter, we're going to have billions upon billions of unstable nuclei. So we usually do get quite a predictable curve from it. Now, one of the things we can tell from this curve is the half-life. And you would have done this at GCSE. Half-life is the time taken for the number of unstable nuclei to decay to half its previous value, or for the activity to drop to half its value. So how we work that out is, I would go to the starting value, there's 80, half of that's 40, so I draw a cross at 40, using a ruler in an exam, and draw it down, and the time that that takes, which is from there to there, we call that t a half, and in this case it's 2 days. However, that's not accurate enough for me. What I do is I take another starting point, and I could start at 40 and go down to 20, but you can start anywhere you like. You can start at 30, go down to 15, you can start at 20, go down to 10. Let's do that. So I'm going to see how long it takes to get down from 20 to half that value, which is 10. And you should see I get exactly the same amount. They expect you to do that twice at least in an examination. And then I would just show that my average is the first one, which was 2, the second one, which is also 2, divided by 2, which unsurprisingly is 2. Show that calculation in the exam. Now, it may be that when you do this off an actual graph, you get something like that, and this then, you do have to take an average of those values because they're different. But even if they are the same, you show that calculation to prove that you've been that thorough in working it out. Okay. Like I say, that's all revision of GCSE, but it's been a long time since your GCSE. So can you practice that by drawing a graph using this data in the table, and then find the half-life for that unstable nuclei A, we've called it here.